Okay. So we'll start today with live session 9. So we'll be covering lectures 25 to 27. Here are some important links as always. And today we'll discuss the module topics in human ecology, which includes 3 lectures. The first one is introduction and impacts, where we discuss about what are the impacts that human cause on the ecosystem and on the globe. The second is human population growth and food requirements. So we see how human population has been growing and changing, how our food requirements have been changing and have been met. And in the third section, we'll talk about sustainable development, which is basically uh, development such that we fulfill our needs while also ensuring that the needs of the future can be fulfilled from the resources that we leave for them. So yeah, so we'll start with week 8. So the first chapter is introduction and impacts. So in this book and also in this other book, basically, these authors have written about how uh, our population is basically going to collapse after some time. And basically, due to limits that are put on population, such as like resource carrying capacity and things like that, human population will eventually lead to a decline and a decrease due to overuse of resources and things like that. So basically, this 1945 is the year that is considered by some scholars to be the beginning of what we call the Anthropocene, because 1945 marks the Trinity test, where basically the US conducted atom bomb testing. So first nuclear tests were carried out across the world, and people realized that the impact that we as a species have on the ecosystem is unrivaled by any other species that is present. So basically, the Anthropocene is a proposed epoch dating from the commencement of significant human impact on the Earth's geology and ecosystems, including but not limited to anthropogenic climate change. So it is still called as a proposed epoch because uh, some people feel like, okay, maybe the nuclear bomb testing was the beginning of Anthropocene, whereas others feel it was the industrial revolution, where humans started having a very significant impact on Earth and its ecosystems. So yeah, so basically because of that, it's written as a proposed epoch, but basically it's the beginning of the time where humans start having a very significant impact on Earth's geology and ecosystems. So what are the impacts that humans have on the environment or on Earth? So the first is overconsumption. So overconsumption is basically, we can define it as greed instead of need. So let's say you can be satisfied with uh, some X amount of natural resource, but always what you want is something more than that. So things like this, and basically disproportionate distribution of resources among individuals also leads to a lot of overconsumption, which is basically overutilization of resources by human beings. The second impact that humans have is habitat destruction, as we have seen before, basically by converting forests into agricultural lands and making more area into converting more area into built up area, or construction work and things like that lead to habitat destruction. Uh, so some things that come under like are similar to habitat destruction include desertification, where basically, let's say due to removal of trees from a given area or like diversion of water from a given area, we lead to creation of deserts or very dry lands in some given areas. Then there's also other things such as ocean acidification, where basically uh, when we release a lot of waste material into the acidic waste material into the ocean, that also uh, leads to increase in acidification, and uh, anything that has carbonate or bicarbonate, if we introduce it into the ocean, it basically leads to ocean acidification, where basically the calcium-rich bodies of sea organisms get dissolved in the water slowly. Uh, Other things such as ozone depletion, so rise in the greenhouse gases such as chlorofluorocarbons and methane has led to corresponding increase in depletion of the ozone layer. So there was a hole in the ozone layer that was created due to human impact, and that we are still trying to get rid of that hole and regenerate the ozone layer, things like that. Then uh, of course, by the use of pesticides and fertilizers, we are basically introducing changes into cycling of various nutrients and minerals, such as nitrogen cycle. And yeah, loss of biodiversity extinction due to human activities, such as uh, poaching, habitat destruction, and other things like that. Um, this habitat destruction and habitat loss and fragmentation also leads to changes in distribution of organisms and corresponding changes in biodiversity. The big impact that humans have on Earth is probably the biggest impact is probably climate change, where basically we are seeing a significant rise in the temperature of the surface of the Earth due to human activity. So the summers are getting hotter and the winters are getting less colder year by year. And this has led to melting of polar ice caps, submergence of some areas of land that were very close to sea level and things like that. Um, and then other changes such as soil erosion and changes in morphology of geomorphology. So basically, uh, what happens basically in a cave. So let's say you have a cave like this. So basically, this cave might have uh, calcareous materials such as limestone or uh, other ores and minerals that are rich in calcium and stuff. So when it rains and there's like raindrops falling, what happens is slowly some of these things get dissolved in the rainwater due to the um, some of these like calcareous materials get dissolved in the rainwater, and they basically slowly start forming these structures. So basically, slowly we'll have something that keeps on increasing. And similarly, due to the rainwater falling down, there's also a deposition of such calcareous material here. So there are things growing out from here. So the upper part is called stalactite, and this part is called stalagmite. So these are natural structures that are generally found in caves, which basically lead to changes in the morphology of the cave. So basically, how the cave is structured, it leads to changes in that. So nowadays, due to construction where we are using a lot of concrete, lime, or mortar, what's happening is you see these stalactite, stalagmite formations even in like basements of buildings, such as in parking areas. If you notice, sometimes you might see if there's a water leakage, there are structures that are coming down from the roof, and there are structures that are deposited on the floor of the building. So basically, these changes in morphology of geomorphology and also soil erosion and other stuff is also something that we humans um, do. The next thing is basically change in stratigraphy due to increased sediment load and deposition. So basically, uh, what happens? We are basically changing the nature of different areas due to our activities such as deforestation or construction activities and stuff like that. So for example, if we have, let's say we have a river here, which basically comes and drains out into a ocean. So we have basically a big delta here that's formed by the river. Now let's say we put up a dam here to store water and convert this area into a reservoir. So what happens? There's not enough water coming here, and slowly this delta begins to shorten, and it basically converts into another habitat, dries up. So Yeah. And at the same time, wherever we are creating the dam, there's a lot of sediment load that is getting deposited below the dam area in that area, and basically the corresponding areas which were earlier the banks of the river will now get submerged. So these changes in stratigraphy are also arising due to human activities such as construction or deforestation. So yeah, other things such as changes in elements in the atmosphere released from fossil fuels, uh, radionuclear fallout also leads to radionuclides and other uh, basically radionuclear elements that then feed into the ecosystem, or basically um, so let's say you have some radioactive waste that gets mixed in the soil, that radioactive material or element is then taken up by plants and then eventually goes into animals, and it can lead to a lot of um, diseases and things such as mutations and cancers that are caused in the um, animals or even in the plants. Um, Mutations, yeah. Then changes in soil, such as water logging. When we have like paddy farms, we basically log it with water. So it leads to a change in the soil moisture content and stuff like that. Desertification, as I said before, by diverting uh, water from certain areas, we are creating deserts there. Then buildup of pesticides and other chemicals. So we have talked about this before also. Things such as bioaccumulation lead to a buildup of pesticides throughout the trophic levels of the food chain. So mm, let's say a goat is basically eating 10 kg of grass. So it's getting all the pesticide that was present in 10 kgs of grass. Whereas a tiger, which might be eating the goat, because the tiger is eating more number of goats. So let's say the tiger eats 3 or 4 goats. Then what happens is it's getting the pesticide not from 10 kg of grass, but from 30 or 40 kgs of grass. So more amount of pesticide is getting accumulated as we move up the trophic levels. So yeah. Then the other thing is introduction of invasive species. So basically, let's say we find some plant that is beautiful or some flower that we like, or let's say some plant which we want to grow for some food purpose or some other thing. We basically want to grow it in some other place, or we want, let's say we go outside and we see this and we want to plant it in our home or something. When we come back, we bring the plant back with us. So basically that leads to introduction of, and if these species are better at utilizing resources and than the native plants that are present there, then basically these will eventually become invasives and take over the native flora and fauna. Examples are lantana and stuff that were bought. So basically Congress leaf is another plant that was brought in by the Britishers, and it has been a very invasive plant throughout the Western Ghats. Uh, then we have things such as pollution, including air pollution, noise pollution, water pollution. So when we let go of waste into the water bodies such as rivers and oceans, it leads to water pollution. Then light pollution is also an issue. So we generally have street lights and other things like that. So basically, in a human-dominated area, there's light even during the night, which is generally not present in areas where human activity is not there. So what happens is this leads to behavioral changes in the activities and activities of different species, and also might uh, lead to changes in like habitat use and things like that. Then coral bleaching and also ORs are things that create a lot of impact on the environment. So how do we measure these human impacts? So just a second. Okay. So how do we measure these human impacts? So let's say, so we have an equation here which describes how a general way of measuring how humans impact the environment. So let's say I is the impact of a human activity on the environment. Then I is given as P into A into T, where P is the population in a given area. So we consider the scope of the activity. How large of an area is it affecting? The area could be as large as the whole world. So P is the population that is involved in the activity or that is present in that given area. Okay. A is affluence. So affluence is basically average consumption of each person in the population. It is generally measured through the values of GDP per capita. So GDP basically indicates how much materials are produced per capita per 1,000 people or something. So so if this much resources are produced, this much manufactured goods or things are produced, that means this is what is also getting used. So that also equals the average consumption of each person in the population, and that is termed as affluence. So basically, anything that we are consuming, any manufactured good is basically adding to the affluence. Then the T stands for technological advancement. So it's basically a measure of how resource intensive the production of affluence is. So how much resource do we need to produce this much amount of um, so yeah, this much amount of resources that we are using. So yeah, so we look at these three things separately: population, affluence, and technological advancement. So population has been rising exponentially in the recent times. So earlier there were not very few people on Earth, like let's say in 10,000 BC or 4,000 BC, there were very few number of people. Um, yeah, then somewhere around like even in the early years, there were early 80s, there were not a lot of people. Let's say somewhere around the Industrial Revolution, where things started getting better. We had better uh, medicine, better equipment, better jobs for people. More people were getting more amount of money to sustain their life and things like that. So eventually, people started reproducing, and the population started shooting up. And now we have close to around 7 billion people, close to, yeah, 7 to 8 billion people on the earth. So, but the thing is, the way this population is distributed across the um, surface of the earth is also very different. And that also affects the impact that humans have on a given area. So, for example, uh, India has a very high population density. India, Bangladesh, and other uh, South Asian countries generally have a very high population density compared to areas such as Russia or let's say Canada. So basically, the effect that humans have in areas like South Asia or let's say some countries in Africa and some parts in Europe would be much more than the effects that humans have on a area such as on a place such as Canada or Russia, because the population density or the number of individuals per square kilometer is very less. So yeah, here's a graph showing what is the population density, which is the number of people per square kilometer of land area in different countries. Even though India has a very high population, the population density of India is very less compared to other countries such as Singapore and Monaco, where they have a lot of people in a very small area. Then, uh, yeah. So to look at affluence, what we generally see is how uh, industry is growing, how manufacturing is growing, how the GDP is growing, and things like that. So we see that throughout, like since 1270 to 1870, and even after that, there has been a increase in industrial output over time across uh, all the industries, all major industries that we have, such as metals, mining, textiles, and leather, and other manufacturing industries. Uh, and we see that the global GDP also uh, is increasing at an exponential rate. So this is from 080 to let's say 2022. How is the global GDP changing? And we see that in the very recent years, which is after 2000, let's say the GDP has been continuously increasing like well beyond from, let's say, if we see, yeah, let's say from this point it has shot up. Let's say it took like almost 2000 years to come to this value, which is around, let's say, 30 million. But from 30 million to like 120 trillion, 30 trillion to 120 trillion, it just took a very few years for the GDP to increase. So the affluence that we are having as a population is also more because we are using more and more resources as time is passing by. Then this graph shows how the GDP per capita value changes across different countries. So in countries such as like USA or Australia, where the values are very high, in some parts of Europe, such as the UK influence, or where values are very high, what this means is more. So these areas have more affluence or more resource consumption than other areas which have lower values, such as most areas in Africa. So this affluence also leads to a greater impact that humans have on a given area or on the earth. So yeah, here it's a graph showing again how the GDP per capita has been increasing, ever increasing since 1820s to 2022, and how it has, uh, for some areas, it has been increasing at a very exponential rate. So especially for Western Europe and like USA, Canada, and all those countries, whereas for other countries such as Africa, it's not increasing that much, but it's still increasing. So the trend is that the GDP per capita is increasing across regions also through time. Then we talk about technology. So technology also is advancing. So we are using more and more transistors per microprocessor. We are using more and more resources to create these chips. As some of you might know or might have heard, there is a global chip shortage now where people are finding it very difficult. Companies are finding it very difficult to find the raw material, silicon, to produce chips, silicon, germanium, and all to produce chips. So there's a like huge demand for these chips as we are uh, now, what do you say, um, trying to use more and more of these chips for things like artificial intelligence, machine learning, and all. But there is a decreasing supply because there's a global shortage of chips and resources to produce chips. But yeah, so the general trend is that since 1970s, when we had um, probably invented microprocessors or transistors. Till now, the number of transistors that are present per microprocessor keeps on increasing. So there's something called as Moore's law, where he basically says that every few years, the um, annual production or annual increase in technology will double. Yeah. So we can see this in other fields such as the computational capacity of supercomputers. So basically, uh, this is the number of operations that a supercomputer can carry out per second. It's expressed in gigaflops. So basically, let's say from 2015, where we have a very low value, uh, from 2015, where we have a very low value, to let's say in 2020, we see a very big jump from, let's say, less than 100 million to over 400 million, and then it keeps on increasing. So yeah, and the other trend that we see, so this trend is also seen in technological advances across fields. So for example, in biology, we can see that the cost of DNA sequencing is getting cheaper. So that is because DNA sequencing is getting more and more advanced and easier to carry out because we are developing better technology. That's why it costs less now compared to before. So here we see that in 2001, it used to cost a lot. So probably over $1 million to uh, sequence 1 billion pairs of uh, DNA base pairs. But now, if we see around 2022, that cost is less than $10. So there's a huge decrease that is driven by the technological advancements in DNA sequencing. So how do we reduce these impacts? We see that um, impact is given by population into affluence into technology. And we see that the population is showing an increasing trend. So the population is increasing ever since uh, the human race has been there. Then the affluence is also increasing because the GDP is increasing across countries and across uh, all across the world also. And the other thing is the technological advancement is also increasing. So the impacts that humans uh, have on Earth or the environment is increasing at an unprecedented rate. So how do we manage that? How do we reduce these impacts? So there's not a lot that we can do based on population, because to decrease population or to maintain population, it will take a very long period of time, let's say 150, 200 years. If you try to basically reduce the population or reduce the birth rate in a given area, it will generally take a lot of time. Then affluence is basically how much can the average person spend, or how rich is that average person, like how much can the average person afford, things like that. So affluence is something that we cannot decrease because we don't want people to become poor and have a substandard uh, living. What we instead have is for affluence to increase as a society so that people have better and better lifestyles, right? So affluence is also something that we cannot in general decrease. Now this technology is where mm, we need to go forward with technology, but we need to be we can possibly change things here to reduce these impacts that we have on the planet. So this can be done by developing technologies that are, let's say, eco-friendly, or basically that are less harsh on the environment, and following practices that basically lead to less deterioration or less degradation of the environment. So, for example, things such as plastic recycling is something that has basically led to a decrease in the amount of plastics that um, are out in the open. So basically, when you take a plastic bag, or let's say a plastic bottle, eventually after you're done with it, what happens to it? So let's say in 2000, what would happen is to almost 60% of these plastics would go into a landfill area. So basically, it's a hole in the ground. They drop plastics there and they cover up the hole. Then the next like 20-22% is basically mismanaged. So it goes somewhere where it's not supposed to go. It goes out into the oceans. Uh, it's lying around the road or somewhere where it's not supposed to be there. Then some part of it is incinerated, so basically burnt out, and very less part was recycled. But now, in 2019, in 19 years, we have seen a steady increase in the amount of plastics that are recycled or incinerated. The amount of plastics that is mismanaged has decreased, and the amount of plastics that are landfilled has also decreased. So yeah, it shows that if we follow strategies such as this, where we are recycling things that hurt the environment, then basically we are improving the quality of the environment while also improving our technological advancement by focusing on advancing on eco-friendly manner. Then the other thing I told about population is that it's difficult to control population all of a sudden. But the good news is that we have crossed the peak growth rates of population. So what does that mean? So what it means is basically generally when you have a population growth curve, it's something like this, right? So where we have a lag phase, then we have a log phase where there's exponential increase. Lag phase is where there's not a lot of increase. And then after that, we have a slowdown, and basically we reach a stable point where the population has reached the carrying capacity. So the number of individuals is equal to the so the resource consumed by the number of individuals is equal to the amount of resources that are replenished across time. Right. So basically, what this means is that we are starting to now enter this zone of decrease. So we were in the exponential phase where the population is increasing exponentially, but now we have entered the uh, final phase where the population growth is decreasing. So here we have plotted basically the population of the world that is in the filled area. So the values after 2015 are the projected values, and the red line basically, or the brown line basically, um, yeah. So the line basically represents what is the growth rate of the population. So it initially increased from, let's say, 0.6 or 0.4% to around 2.1%. And now around 2015, it has fallen down. So we are seeing that the growth rate is decreasing. So eventually this growth rate will come down to, let's say, zero. And after that, the population will stabilize, like we'll reach this final phase. Okay, so that's a good news. So even if we are not doing any population control, we have already crossed the peak growth rate. So the amount of growth that we see now will not be very unprecedented or will not be very exponential. The other thing that we see is across the globe in different regions, we see that the fertility rate is decreasing. So the fertility rate is expressed as a number of children per woman. So basically, this is also decreasing because more and more people are marrying late, more and more people are getting educated, more and more people are having less children compared to before. Earlier, people used to have six, seven children, but now people are preferring to have one or two or maybe no children at all. And that's why this is leading to a decrease in the fertility rate. So that is also a good thing, because that also will lead to a slowing down of the growth of the population and basically help our population to stabilize after a point. Uh, yeah. So the other thing is the growth rate. So basically, these are three age pyramids. The first one is the inside one here, which is for 1950. The second one is the um, darker one, which is 2017. And the outline is basically 2100. So what do they see? So this basically on the x-axis, after zero towards the right, we have the number of men in the population. Towards the left, we have the number of women in the population. And on the y-axis, we have different age groups. So basically, this is from 0 to 10 years, 10 to 20, 30, 40, and so on till 100. So what we see in the 1950 population is that it's a growing population. So because the base is much wider than the top. So the base here is much wider than the top. So there are a lot of individuals that are getting born, that are new, that are infants, which will basically enter the reproductive age and lead to more reproduction. And there are very few individuals sorry, which are of the older age. Okay. Then the other thing we hello, hello. Can you guys hear me? Hello. hear me? Can someone reply? There's a power cut. I'm not sure if you guys can hear me. Uh,
Sir, we can hear you, sir.
We can hear you,
oh,
sir.
okay. Thank you. Yeah. So the other thing that we see in the 1950s graph is that uh, since there are more number of individuals in the bottom layers, but we see as we go up, the number of individuals falls rapidly. So there's a high mortality rate. So there's a high birth rate and there's a high growth death rate in this population. So yeah, basically the population is going to increase, but uh, like more number of individuals are also dying. Then the next one we see is for 2017, where we basically see that now we have more number of individuals. That's why the graph is bigger. So initially we had close to around 40 million women and 40 million men. But now in 2017, we have greater than 60 million men and 60 million women, like infants, right? In this lowest run. So here we see that now the death rate is slightly lower because now the steepness is decreasing, whereas here it was very steep. Now it's decreasing. So, and also we see that the average life expectancy of the population has increased because here there are no individuals after, let's say, 75 years in 1950, but here there are individuals still around 100 years in 2017. Right. Then 2100 is the projected growth, where basically mm, we will have this tapering at both sides. So the birth rates will decrease, and that's why we'll have less number of individuals in the lower age groups compared to before, where in 2017 we have more number of individuals still in the lower age groups because there's still a very high birth rate. But now the birth rate will also get lower, is what is being predicted, and therefore the rate of growth of the population will also decrease eventually over time. So it's slowly reducing, and yeah, basically it will keep on decreasing, is what is projected. Yeah, so in short, there's nothing we can do about affluence. Affluence needs to increase over time. As a society, we develop that way. As a civilization, we develop that way. Uh, Technology is getting better, but and we have other methods, alternative things which we can basically do and use to help nature or help mitigate some of the effects or effects that humans are having. And population is um, not declining now, but the growth rate of population is declining. So eventually, this will lead to a stable phase after a few years. Okay. Does anyone have any questions?
No, sir.
Okay. So the next chapter was on human population growth and food requirements. So basically, we talked about this guy, Thomas Robert Malthus. We talked about him earlier also. He was English cleric and scholar who basically wrote a book and essay on the principle of population, which influenced a lot of studies in population ecology. And he also gave his Malthusian growth model for human population. So basically, what he says is that human population grows in a geometric progression. So roughly every 25 years, the population is doubling. So one individual becomes two, two becomes four, four becomes 8, 16, 32, and so on. Ideally, like in sexually reproducing organisms, we start with two and not one. Uh, then he also says that food supply, on the other hand, increases in arithmetic progression. So if the food supply is like, let's say one, then it increases to two, three, four, five, six. So it increases in arithmetic progression, not in geometric progression. So yeah. So thus he says that population tends to overrun the food supply because so let's say we have in the second year we have 2 million individuals here, And in the third, fourth, fifth year, we have 16 million individuals, right? Here, whereas if we have, let's say, 2 tons of resource in the second year, then three, fourth, fifth year, we will just have 5 tons of resource. So when we have 2 million people, we had 2 tons of resource for them. But now we have 16 million people and we have 5 tons of resource. So eventually the population is going to overrun the food supply because the food supply is not increasing at a rate that at which the population is increasing. So he says that this imbalance is corrected by positive checks such as vice or crime and all, misery, where people are poor, then famine, war, diseases, pestilence, flood, and other natural calamities. So these are the things that basically keep population in check, uh, population of humans in check, so that basically we don't overrun the food supply. And he says that as a species, if you want, we can also use preventative measures or checks to fix this imbalance, such as foresight, late marriage, celibacy, moral restraint, and so on. So this is what Thomas Robert Malthus told long back. But is this true? Is what people uh, try to figure out. And we have seen that the population does show exponential growth, as Thomas pointed out. So basically, if what he's saying is that two individual becomes four, four becomes eight, eight becomes 16, 16 becomes 30, 16 becomes. Hello? Okay, yeah. 16 becomes 32 and so on. So basically what he's saying is the population at time t plus 1 is dependent on the population at time t. So if there are more individuals, then there is more population increase in the next time step. So basically what we can say is the change in population is proportional. So basically change in population is proportional to the population at a given time. Right. So let's say you have 1000 individuals, the number of individuals that you will get will be lower than if you had 1 million individuals to begin with. Right. This will be higher and this will be lower. Right. So the rate of growth of population or the rate number of births per year or things like that basically depends on the population size. So what we have done is we have put a constant k, which is a positive constant, to denote this equation. So dp by dt equal to k into p. Now, if we integrate both sides, what we get is Pt is given by P naught e raised to the power k into t, where P naught denotes the population at time zero, and this shows that it's a exponential growth model. And we see that world population does show exponential growth. So was Malthus correct? Okay, that's a question that arises. The other thing is that we generally check when we are looking at population studies is something called doubling time. So doubling time is defined as the time required to double the population size. So let's say from 2 to 4, from 4 to 8, and so on. So thus, we have population at time dt will be equal to twice of P0, where P0 is the population at the initial time. So let's say we start from 0 and we go to time TD. So the population here was P0 and now the population is PTD. So since PTD is the doubling time, the population here will be twice of what it started out with. So twice of P0. And then basically for substituting the equation that we have here from the Malthusian growth model, we get P naught e raised to power k dd is equal to 2 into P naught. Now P naught cancels out. We have EKTD is equal to 2, and if we take log on both sides, and we basically do some shifting of variables from here to there, see that doubling time is given as 1 by k into log of 2. Now we know that log of 2 is a constant, and we know that k that we took here is a positive constant, right? So the value of k is also a constant. That means our TD is also a constant value according to the Malthushian population growth model for humans. Okay, because we are using that equation here. So there are multiple criticisms. So the first thing that people say is the population growth is not as suggested by him. So Malthus suggested that the population doubling time is 25 years. However, going from data, we see that the population doubling time is not exactly 25 years. And the other thing is, according to his population, this doubling time should be a constant value according to his model, because he's defining the population as an exponential growth, uh, pop exponentially growing population, right? But we see that the doubling time also changes across time. So, for example, in 1543, it took almost 697 years for the world population to double, right? From 0.25 billion in 837 to 0.5 billion in 1543. Then if we look at here in 1803, we see that to for the population to go from zero point 0.5 to 1 billion, it took around 269 years. However, if we come to recent times, we see that the population takes much shorter time to double. So for example, in let's say 2000, we can say that the population took around 37 to 40 years to double, right? And in 2024, it took only 49 years to double from 4 million to 8 billion, 4 billion to 8 billion, right? So we see that the doubling uh, time is not constant, and it's not uh, what Malthus has put forward, which was 20. Right. But we see that the doubling time is decreasing as we pass through time. But the thing is, if you look at this graph closely, you will see that after a point around the 2000, the doubling time is also increasing. So that means the population is transforming and the growth rate is decreasing. Right. So generally, this is what is suggested to happen in human populations. So basically, there's something called demographic transition, which occurs in populations. So the first step stage is where there's a very high birth rate and there's a very high death rate. So sorry. So this is, let's say, imagine times much before industrial revolution, much before uh, like long back when, let's say, populations were hunter-gatherers or they just started doing agriculture and things like that. So what happens is there's a very high death rate in the population because a lot of individuals are getting sick and dying off, or they're going out hunting and dying off, and things like that. So to compensate for this high death rate, this population also has a very high birth rate because individuals are now producing more and more children because some of them keep on dying. So if you look at the population pyramid for the stage one, we see that the population pyramid is like a concave triangle, right? Slightly like this. Hmm. So what is happening is basically there are more children that are born, but many of them die off. That's why the number of individuals in these age groups decreases. Right. So to compensate for these for this death, there is a very high birth rate. Then what happens is in stage two, due to advances such as it's a better medical uh, facilities or maybe uh, like discovery of initial antibiotics and things like that. Now we are beginning to basically treat diseases and basically uh, take care of other people who are injured during hunting and all that. So the death rate is now falling rapidly. So the death rate is decreasing, but the birth rate is still the same because there's no incentive for the birth rate to decrease right now. Right. So now what we have is something like a triangle. So basically what is happening is it still has a very high birth rate because the base is much wider than the top, but the uh, not wider than the top because but because the base is much wider, it has a very high birth rate, but still but the death rate is now decreased because earlier only this much amount of children, let's say, survive till 10 years, but now additionally this much and this much are also surviving. Right. Then we basically see the stage 3 of demographic transition, where basically the birth rate also starts to fall. So let's say things like late marriages, people getting educated and things like that, they are starting to like, or maybe the cost of living has increased and therefore people cannot afford to have that many children because like they're not dying anymore and you need resources, more resources to feed 5 children than you need resources to feed two. Right. Earlier, if you had 6 children, 5 of them would die, so you just have to feed one. But now you have to feed all six if you make 6 children. So therefore, the birth rate also now starts falling. People start having less children, and therefore that leads to what we see here in this graph, basically flattening of the curve here. So basically, the number of newborn children are not that much greater than the number of uh, children, and let's say maybe the starting of the reproductive population, right? And then slowly what happens, we move into stage 4 where we have both very low birth rate, very low death rate. So the stage 3 is the part where we are currently in. Stage 4, it's predicted that like uh, basically what do you say, we have very low birth rate, very low death rate, and therefore we have a now because we have a very low death rate, we have a graph something like this, which is rounded on the top side. So not a lot of people are dying as here as before. So here a lot of people used to die, but now very less people are dying as they grow old. And eventually, what will happen is the birth rate will slowly rise, but the death rate will still be low, and there'll be a very stable population. So we are currently in stage 3 where basically increase in the slowdown. So the population growth has started to growth rate has started to decline, but the population has not declined yet or become stable yet. So that is coming up. Right. So not according to what Malthus said that we have exponential growth where basically our human population will keep on increasing like this. We see that our population is not increasing like that, rather it is increasing like this. And we are currently at this phase of slowdown. Okay. The second criticism that people have is basically the agricultural growth is not as suggested. So Malthus suggested that agricultural growth is um, arithmetic. So it's basically uh, increasing very slowly over the years. Right. One becomes two, two becomes three, four, and so on. We see that till some point, till let's say 1960s to 2000, the growth was maybe very slow. So the global cereal production was maybe not that much, but it has been slowly increasing over the years. But now what we see is that if we factor in recent years, we see that there has also been a very large exponential increase in the growth in the agriculture also. For example, different crops like wheat, barley, and oats, we are producing them in much more quantities now compared to how we were producing them before. So this agricultural expansion is also not what do you say, arithmetic as Malthus suggested, but more exponential now in the recent years. Right. The third thing is that it does not incorporate new land that becomes available. So this is basically a graph showing how much of the land on Earth is used for different uh, purposes. So we see that uh, croplands are basically places where we have crops that if you put all of them together, they'll probably be as large as China plus a few of these other countries in Southeast Asia. Whereas livestock, the area of land that is used by livestock for livestock farming and cattle farming and things like that is much larger, encompassing, let's say, both North and South Americas. Right. So almost one third of the area of the earth is used for cropland and for livestock activities. And some area is also used for, as built up area, which is basically our construction, homes and all that. Right. Whereas some area is still left for forests. So 26% of the area is left out for forest, and this 8%, which is representative of like, let's say the area of Australia and other countries is maybe shrublands, and most of the other part of area, which is 19%, is basically barren lands, and we have some glaciers that are present. So basically, this so the land on Earth is used for different things, and there are different resources and different things that are present on the land, such as forests, shrubs, glaciers, freshwater area, barren land, and also areas that are used for agriculture, such as cropland and livestock. So cropland and livestock, both of them are included in agriculture, right? And so what we see is that the amount of area that is used for agriculture is quite high in a lot of areas, such as, let's say, in China or India. Right. Um, we also see that across the different regions in the globe, it has been increasing across time. So there's been very large, even exponential increase in the amount of area that is used for agriculture over time. So this means that we are producing more and more resources, more and more food for people. So the amount of food that is produced is also not limited, as Malthus did not basically account for this increase in the area that we might get. So more and more land that is converted for agricultural land is now used to create food and resources to satisfy human requirements. Like, we also see a corresponding increase in like areas with croplands and areas with uh, grazing areas basically. So this basically is another criticism of Malthus, where basically people are saying that he did not take into account that thus changes or increases in agricultural area is also something that will happen, that is happening. And the fourth thing is people say that he neglects the role of technology. So basically this exponential increase in the yield of plants that we see in the very recent years is mostly a direct uh, basic, result of basically increased technological advancement. So now we have better strains of crops that we are growing that require less resources to grow or less management to grow. And we have better pesticides and things like that, which basically prevent our farms from dying off. Right. So basically, the amount of pesticides that are used per hectare of cropland is also very high in a very in some areas where there's a lot of farming, intensive agriculture going on. So that also leads to an increased yield because very less plants are dying from diseases or pests, and therefore we have more productivity or yield of the area. Okay. So we see that the pesticide production and pesticide imports are also increasing across years. So the blue points here denote the pesticide production. So across the years, the production of pesticide is also increasing globally, where and the import of pesticides across countries is also increasing. That means more and more countries are using more and more pesticides as the years go by. Then the other thing is the introduction or improvement of fertilizers, which basically increase the yield of a given area of land by making more nutrients available to the land. Right. So the amount of fertilizers that are consumed across the years has also kept on increasing steadily. Right. Uh, then basically these fertilizers for different uh, compounds are also increasing. And also we see an increased use of water in agricultural practice across the years. Here we see what is plotted is basically on the y-axis, we have the yield of cereal or yield of the crop. So how much of food is produced per unit, how much of food is produced basically. And on the x-axis, we have the use of fertilizer, how much nitrogen fertilizer are they using. So this is a log graph. So basically each line here. So basically this is 0.1, this is 1, this is 10, this is 100 and so on. And here again, this is 0.1 tons, this is 1 ton, this is 10 tons, right? So this is a logarithmic graph where basically the each line is basically 10 times the line before. It's not increasing in a linear fashion. Now here we see that for different countries, we have plotted how much fertilizer they are using and how much cereal is yield, how much is the yield of the country. Now, if we try to fit a line through it, it will probably look something like this. Right. So what does this tell us? This tells us that there's a positive relation between fertilizer use and cereal yield. So as more and more countries are using more and more fertilizers, they are also seeing increased yields of cereals or increased production of food. Right. The other thing is this increase in things such as fertilizers and what was the other thing? Yeah. Pesticides and fertilizers are basically leading to an increase in production of uh, resources and crops and basically livestock and basically increasing yield. So the amount of land that is needed to produce the same amount of um, what is it? Same amount of crops has steadily been decreasing over the years because of this. So what does this mean? So this means basically, let's say to produce 100 kg of some crop, you needed, let's say, 1 hectare of land, right, in 1960s. But now, in let's say 2021, you need somewhere around, let's say in the 2000s, you need somewhere around 0.3 hectares of land to produce that same amount of resource, which is 100 kg of the cereal. So what does this mean? This means that as our technology is advancing, it's becoming easier and easier for us to produce more crops and get more productivity from the same amount of land. Right. But this also means that this does not mean that the amount of land that we are using for agriculture is decreasing. So the amount of land that we are using for agriculture is increasing as we saw here. So the area that we are using is increasing over years, and also the productivity is increasing. So we are producing more and more crops from the same amount of area that we had before, right? Because our demands are also increasing. So there are other criticisms, such as population is not related to food supply, but to total wealth. So what people say is that the growth of human population is not driven by the food supply, but rather by how much money a certain population of humans has, uh, a certain population has. So because money is the thing that leads to you getting access to resources. So in a way, money or wealth is basically the driving factor behind population. and not food supply. The second point is it does not consider the population increase due to the lowering of death rates. So basically, um, what do you say? As the years go by and as we are getting better and better at um, better and better at medical facilities and developing more and more treatments for things, uh, there's a lowering of death rates. Uh, Basically, that is also leading to a increase in population as less and less people are dying over time. Right. So this is also something that is not considered in the model. The third thing is preventative checks do not pertain to only moral restraints. So now we have contraceptive methods and other things, sterilization programs and things like that, which basically lead to a decrease in population. So these might not only be dependent on moral restraint. And the fourth thing is positive checks may also occur in low populated countries. So what Malthus said is that positive checks, such as natural calamities, floods, and all, generally occur in areas which have very high population. But we see that even in low populated countries, such as in Japan and all, there are a lot of earthquakes, lot of floods, tsunamis, and all that happens. A lot of natural calamities. So that does not line up with this theory. Okay. So this section was mostly about Malthusian's theory of how population growth grows and how basically uh, our population is doomed because we have geometric growth of human population, but arithmetic growth of resources that we are using. But we also looked at how these claims might not be true and why there are certain factors that indicate that probably this theory is outdated and we need something better. So the next part was sustainable development, where um, basically, as we talked before, okay, before that, does anyone have any questions? Huh, sorry. Hello. Does anyone have any questions? Okay. So, as we learned before in the previous lecture, how we quantify human impact is basically by these three things. One is P, which is population, A, which is affluence, and T, which is technology. We saw that technological advances can basically lead to uh, better technologies and more eco-friendly technologies, as we talked about, which basically have lesser impact on the environment. The population rates are mm, slowing down, growth rates are slowing down, and thus the population of humans will eventually stabilize after a few years. And we also noted that affluence is something that we cannot decrease as a society because we want people to have more and more access to resources and become more and more wealthy in terms of getting resources. So uh, we have what is called a production possibility curve or a production possibility frontier, PPC or a PPF, right? Uh, Basically, what this tells us is, let's say we have some resource and there are two items that we can manufacture using that resource. Right? So let's say we have some money that we can either give to companies that manufacture laptops, or basically we have some money which we can give to companies, basically farmers who are creating growing cereals for us, for us. So based on how much of what we want, we can distribute our allocate our resources such that we have optimized production. So let's say in an area where we have basically no place to do agriculture or no farmers present, we can allocate all the money that we have for laptops, which might be more useful for the population. Whereas in an area where there's a shortage of food, we might want to invest more money or resources into uh, agriculture and growing cereals and food items. So this line here basically represents the production possibility curve or the production possibility frontier. So let's say you have you just put some numbers here. Let's say you have 1 million rupees, and you basically, if you put all 1 million rupees, you arrive and you make laptops, you arrive at point A, which is, let's say, 500 laptops, right? But if you put all the money and you basically uh, manufacture, not manufacture, grow crops, basically you have, let's say, 10,000 kgs of cereals or crops that you can grow. So this point, so let's say there's some point here where you have, let's say, 5,000 kgs of cereal that you can produce and 250 laptops you can produce. So this will also use up all your 1 million rupees, but this is now distributed in a way that you get half of this and half of that. So all the points here that lie on this line basically maximize the use of the resource. So all of the resources used either to produce A or to produce B. So in this point, we are producing this much amount of laptops and this much amount of cereal. So let's say we are producing 2,500 kg of cereal and we are, let's say, producing 400 laptops here, right? So we are using all the resources that is available to us. However, if we choose a point here, what we are doing is we are basically producing, let's say, 200 laptops and 3,000 kgs of cereal. And basically, uh, we are using part of the resource. We are not using the full amount that we have. We are using just a part of that because this point falls under the curve. And the rest of the part we are saving for later use, or let's say we can invest it in some other thing. And the other thing about this production possibility curve is that we cannot go beyond a point that is um, go to a point that is lying outside of this curve because we don't have the resources. Okay. So as we saw before, this production possibility curve, where does it come in place? When we are making a choice. So when we are basically choosing to produce something or something else based on how much it's affecting what our needs are and how much it's affecting the environment and things like that. So one example that's talked about is basically, let's say we have factory A that produces pens and sells it for 10 rupees, right? So factory A is just producing pens. So it's taking some raw materials, basically producing pens, and it's leaving out some toxic waste material that it's basically uh, putting into ponds and everything. Right. So this is situation one. And the second one is factory B. So here we are producing manufacturing pens for 10 rupees. Then what happens is the waste that this plant produces or this factory produces is then treated before putting it into ponds or oceans or lakes. So what this treatment also costs 10 rupees. So now factory B 10 sells pens for 20 rupees, whereas factory A sells pens for 10 rupees. Right. So basically now we have a choice whether between affluence and environment. So what this means is, let's say the average person has 100 rupees. Right. So if the average person buys pens from this factory or from this company, the person can buy 10 pens in 100 rupees. Whereas if the person is buying pens from this factory, the person can buy 5 pens. So the affluence in the second case is decreased because there is less number of resources that the average person can afford. Right. But in the second case, since we are treating the waste before uh, putting it out into ponds and lakes and other places, what is happening is the environmental value is increasing. So we are not basically causing more, we are causing more damage to the environment in the first case, whereas causing less damage to the environment in the second case. And we are having more affluence in the first case because the manufactured item is cheaper, whereas in the second case, we are having less affluence because the manufactured item is more costly now. Right. So sustainable development is basically this idea taken to a large scale. So basically, what sustainable development means is the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So basically, we are meeting whatever needs that we have and we are not compromising on the needs of future generations. So in the first case, when we are putting this waste material into ponds, lakes, and rivers, what is happening is we are degrading the habitat there. And probably that might lead to a decrease in the amount of fishes that we might have. So basically for future populations, what it's doing is it's leading to a decrease in the resources that they can utilize. But in the second case, that is not the case. We are treating the plant water before sending it into lakes, rivers and ponds, and therefore the water is harmless. But this increases the cost for us, right? So there's a trade-off. Now, sustainable development, this definition has two key concepts. So the first one is the concept of needs. So in particular, the essential needs of the world's poor, to which overriding priority should be given. So basically, we should be able to differentiate between need and greed. So basically, need is something that we absolutely need. So, for example, food for poor children, poor people, starving people, let's say people in third world countries and stuff like that, where they don't have enough resources or enough money to get food, things like that, clean drinking water for everyone. So, these are basically needs. And essentially, in this large framework, they basically refer to the needs of the world's poor and people priority should be given to like world's poor and then to people who can afford a better life. And the second is the idea of limitations imposed by the state of technology and social organization on the environment's ability to meet present and future needs. So basically, what we are saying here is that the resources that we have are limited. So we cannot basically fulfill both our affluence and uh, basically meet our future needs at the same time. Therefore, we have to restrict our affluence to our needs and basically use only whatever we need and save the rest for our future. Hmm. So there are three pillars of sustainability. The first is environmental sustainability, the second is economic sustainability, and the third is social sustainability. In environmental sustainability, we have things like ecosystem services. So what ecosystem services can we provide? Then green engineering and chemistry, where we basically have more eco-friendly materials uh, that are developed, such as biodegradable plastics and stuff like that. Then air quality, water quality, so reducing the amount of air pollution, water pollution that we create by treating waste, water waste, and basically air waste that is coming out of factories and things like that. Then reducing the effects of stressors like greenhouse gas emissions, pollution. So basically all the things that have already been done, all the greenhouse gases that have been emitted, how can we reduce the effect of that so that we can reduce or alter the effects of global warming and climate change? Then basically resource integrity by minimizing waste generation. So what to prevent accidental release in the future. So what this basically means is that let's say you are uh, generating some waste now, but you're not treating it properly. So you're just storing it somewhere or keeping it away from some place that is away in some place that is not used right now. But what might happen is in the future, it might get released into more areas or more places because it is stored and built up in a given area. So what this point means is basically you minimize the waste generation by treating the waste so that it's not harmful before you release it. Right. The next pillar is social sustainability. So this is basically uh, environmental justice and empowerment of communities burdened by pollution. So uh, let's say pollution is affecting a certain population of humans or certain communities, then we should be giving more basically they should be given justice and empowerment. So what does this mean is basically, let's say uh, there are a lot of um, manufacturing that is going on in, like, let's say um, China. So there's a lot of pollution that is going on in China because of that manufacturing. And but this manufactured products are basically exported out and used by the people staying in the rest of the world. So the benefits of the manufacturing is received by people who are different than the people who are incurring the negative impacts of the uh, manufactured commodities or basically things that are produced. Right. So the population in China is the one that is suffering from, let's say, air pollution and things like that due to high number of manufacturing uh, industries that are present. But the other areas are gaining profits. Similarly, for anything that is set up in Bangladesh or India, or any plant or any manufacturing plant that is set up. So basically, so we as a group basically have some what do you say? Have to bring these communities, such as these people who are affected by these pollution and stuff, to justice and basically give them a better life. Another example can be when we are building a dam. So when we are basically building a dam, we are basically changing a very large part of the area, making it into a reservoir. Maybe there were villages here which used to get water, but now they are not getting water because there's a dam. Or there are villages here that used to be there on the banks of this river before the dam, but now due to addition of the dam, this whole area is converted into a reservoir, and basically the villages are submerged. So giving them new houses or giving people who are downstream from the dam access to water. So these are things that are environmental justice, or basically things that should be uh, provided to these communities. And empowerment is basically including them in things such as decision making before making a dam, making sure that people there know that a dam is being constructed and how it will affect them, and they should have a role or a say in if that dam should be constructed, if this company or industry should be set up, and things like that. And then the third point is protection, sustenance, and improvement of human health. So basically, socially, we are bound to improve human health so that everyone has a sustainable life. Next, education about sustainability so that people know. So only people who are educated are people who can raise their voice and basically, let's say, talk to other people, their representatives, such as MLAs, MPs, and all, and make change happen. So this education about sustainability is also something that needs to be done. Protection, maintenance, and access to resources and promotion of sustainable living are also things that come under social sustainability. The next thing is economic sustainability. So basically, even if we mm, go forward and basically lead sustainable life, people need to have a job, people need to have something to do, some way of earning money, so people need job security. Then sustainable practices are should generally be incentivized. So there are things such as Pigovian taxes and subsidies. So Pigovian taxes are basically taxes that um, what do you say, are levied on things that are harmful or things that people want to practices that or methods or processes that are what do you say, that want to be de-incentivized and reduced. So, for example, taxes on things like smoking, gambling, and alcohol. So these are basically Pigovian taxes where you're paying more money because you're using something that is harmful to not just you, but also people around you due to passive smoking and all. Then Pigovian subsidies are basically similarly like incentives or benefits given to sustainable practices or sustainable projects, such as subsidies for like farmers, subsidies for education, building a school, and things like that. Market practices for sustainability, then like natural resource accounting. So basically, accounting for how much of natural resource is being used and how much we are leaving out for the future and how we can balance that. Then life cycle cost assessment, which basically includes assessing all the positive and negative factors that a given object or a given product has, including the positive and negative externalities. So externality is basically a second-hand effect that a object has on something or a practice has on something. For example, passive smoking is a negative externality of smoking. So people who are smoking generally affect the other person who is present nearby using in a negative way due to smoking. So that's a negative externality. Then plastic bags, for example, uh, plastic bags going out into the ocean or getting thrown, plastic bottles getting thrown in the ocean and then ending up in like uh, turtles' diet and all and affecting them. So basically, turtles die if they eat plastic, and there are other animals which are found to die when they're ingesting a lot of plastics. So this negative effect that it has on other environmental flora and fauna should also be used to assess the cost of a given bag, a given thing. So, for example, uh, let's say you're buying a plastic bottle of water for let's say rupees 10 only, but that is only including the manufacturing cost and the cost it takes for the water to not the manufacture, the packaging cost and basically the cost of transport of the water to you. But what life cycle cost assessment says is that you should include all the positive and negative externalities. So, for example, the amount of let's say economic value of how much pollution it is causing, how much drains or pipelines are getting clogged due to plastic waste, and how much turtles are dying and things like that. So if you put those costs are also assessed to the uh, way to put a price on the material, then probably that uh, price would increase quite a lot, right? Because the thing becomes now more expensive because it has more negative externalities or negative influences. Right. Then the last point is cost structure to reduce risk and promote new technologies. So, for example, let's say the government wants people to adopt the solar uh, these are solar panels and solar energy. So what the government can do is basically, what the government is doing in some places is basically giving people incentives so that if you get a solar panel in the day, you can generate a lot of electricity, some of it which you will use, and the rest of it, whatever electricity is not being used by you, but has been generated by you, can be sold by you to the government at a subsidized price. So basically, they are saying that even if you have to invest a lot of amount of money to set up a solar panel now, eventually in 5 or 10 years, it will give you back the returns. So there's some cost structure that can reduce the risk of uh, basically adopting solar panels and promote more people or what do you say? Mm, More people they can basically promote this technology to more people so that more people adopt it. Based on these three pillars, there's something called the triple bottom line, which is basically accounting framework with three parts. Uh, so generally, when you are accounting or you're, let's say, calculating the value of a company, valuing a company, you generally look at the financial aspect, whether they're getting some loss, whether they're getting some profit, and all that. But this triple bottom line approach, what it does is it has three parts which are used for the accounting. So the first is social, which is basically things relating to the social sustainability. So basically, is this company empowering communities? that are present nearby? Is it providing for education or maybe spreading awareness in these communities and basically other things, other social things that the company can do? Then environmental or ecological, which is basically how much of the natural resources are being destroyed, how much natural resources are being replenished, or like if it's a mining company, let's say it's mining somewhere, what does it do after after it has done with after it has been done with the mining, right? Does it reclaim the land area, or does it enhance another area of forest nearby? Right? And also financial. So these three things are taken into account to give the triple bottom line of a company nowadays. Now, there are two things that we need to distinguish. So the first is weak sustainability, and the second is strong sustainability. So weak sustainability is basically assumes that natural capital and manufactured capital are essentially substitutable and considers that there are no essential differences between the kinds of well-being they generate. The only thing that matters is the Okay, so weak sustainability assumes that natural capital and manufactured capital are essentially substitutable and constitutes that there are no essential differences between the kinds of well-being they generate. Okay, so what does this mean? So if we go back to our example of, let's say you have a forest in a given area, right? And basically what you do is you convert it, you cut the wood, and basically in that same area, you build a house using that wood. Whatever. Build a house. Okay. So according to weak sustainability, both of these things are considered substitutable. So you can basically cut this forest and place a house, uh, and there are no differences between the well-being that they generate or the effect that they have. Okay. The only thing that matters is the total value of the aggregate stock of capital, which should at least be maintained or ideally increased for the sake of future generations. So if the amount of, let's say, aggregate stock capital can be something like money, the amount of monetary benefits that you derive from this in terms of, let's say, fruits and all, if that is compensated for by the presence of this house, then basically this change is not something that should bother anyone, is what weak sustainability says. Right. In such a perspective, it does not matter whether the current generation uses of non-renewable resources or dumps CO2 in the atmosphere, as long as enough machineries, roads, and ports are built in compensation. So basically, it doesn't matter if you harm the environment, as long as what you get out of it has uh, can be like monetarily compensated, like can monetarily compensate for the things that you are destroying. So in this case, like the pen example that we had, basically factory A and factory B, weak sustainability would consider both of them to be sustainable, because factory A, even though it is producing a lot of waste, it's generating pens that are of economic value, and that's why uh, this because this manufactured good that is pen and the raw material that it uses and the waste that is generated, it generates a substitutable. And basically, the only thing that matters is how much growth it's causing, like how much growth the stock of capital is increasing, how much money is increasing, or how much the value is increasing. So that means it does not consider that factory A to be non-sustainable. Factory A is sustainable because it is producing something that has some value, even though it's degrading the environment. We don't care about that. And factory B, again, is sustainable because it produces something of value, and it also maintains the environment. Right. So weak sustainability would consider both of them to be sustainable. So now we look at strong sustainability. Strong sustainability assumes that natural capital and manufactured capital are essentially non-substitutable and considers that there are essential differences between the kinds of well-being they generate. So what this means is basically, according to strong sustainability, let's say you have the forest, right? And you're planning to convert it into a house. So strong sustainability says that these two things are not substitutable. Right. So you cannot just cut up these trees and place a house here like it's the same thing. It is not. Right. So the kind of well-being that they generate, both of them generate, are different. Strong sustainability also says that both natural and manufactured capital need to be at least maintained or ideally increased for the sake of future generations. So what this means is, for something to be sustainable, in strong sustainable, according to this definition, what it should do is both either maintain this both or increase the value of both of these. So in this case, our factory A will not be sustainable because it is decreasing the quality of one resource, but factory B will be sustainable because it's maintaining the quality of a resource, but also producing something or manufacturing something that is of value. Here are some differences between strong and weak sustainability. So the key idea is that the substitutability of natural capital by other types of capital is severely limited in strong sustainability. Whereas in weak sustainability, we say that all these different types of capital, natural capital or manufactured capital and all, are perfectly substitutable. So you can replace one with the other. Then the consequences of this for strong sustainability is that certain human actions can entail irreversible consequences. So if you get rid of a given, let's say, uh, forest area, then basically, not a forest area, let's say you basically uh, mine through a given area where there was a forest earlier. And after you have mined, you cannot plant a forest there because the ground is now very loose and there are holes in the ground, like caves in the ground, right? So basically, some certain actions carried out by humans can have irreversible consequences, whereas weak sustainability says that technological innovation and modern monetary compensation for environmental degradation is good enough. So as long as we are getting some value out of it, as long as we are getting some good like minerals that are mined from the mine, it's okay to cut down the trees and basically degrade the landscape. The For strong sustainability, the sustainability issue is conserving the irreplaceable stocks of critical natural capital for the sake of future generation. For weak sustainability, the sustainability issue is the total value of aggregate of the stock capital, both natural and manufactured, should be at least maintained or increased for future generation. The key concept for strong sustainability is critical natural capital, which is the natural capital, natural environmental resources that we find. And for weak sustainability is the optimal allocation of these resources or these scarce resources. So even if you manufacture or modify some of them, even if you get rid of all trees to build houses, it's okay as long as the value of houses is greater than the value of the trees that were there before. Great, monetary value. Then the last thing is basically how they define thresholds and environmental norms. Strong sustainability says that scientific knowledge should be used as an input for public deliberation. So scientific knowledge should be used to basically uh, deal with sustainability issues and figure out work plans for sustainability. Whereas weak sustainability says that uh, technical or scientific approach to determining the thresholds and norms is enough. So once you determine how much of this resource you can use without causing that much damage, you should stop there and use it. Whereas strong sustainability says that even if there are limits, we should be able to find better methods or maybe develop more scientific knowledge to better uh, create manufacture items and better use resources. So based on these sustainable development, uh, so this is the Agenda 21 was basically a Earth Summit that was conducted in Rio by the United Nations. where they basically set sustainable development goals for the 21st century. Then they have um, regular meetings where basically these sustainable development goals for different countries are presented and basically followed up with. So there are 17 sustainable development goals, such as no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, and other things such as reduce inequalities, life below water, life on land, climate action, and peace, justice, and strong institutions. So these are the different sustainable development goals, and there are different work plans that countries have proposed, and policies and changes that have been made towards these sustainable development goals. One such thing that is generally carried out for uh, any basically proposed project or development plan is the environmental impact assessment, or EIA. So the environmental impact assessment is a process of evaluating the likely environmental impacts of a proposed project or development, taking into account interrelated socio-economic, cultural, and human health impacts, both beneficial and adverse. So basically, it's assessing what is the impact of this proposed project or development in accordance with both all three socio-economic, cultural, and human health impacts, both impacts which are good and bad for all these three aspects. So what happens in EIA? So there are different stages. So the first is screening to determine which projects or developments require a full or partial impact assessment study. So if you have a very small project, let's say you are just setting up a small manufacturing plant in a small warehouse where you are not producing a lot of waste. mm, let's say you're setting up a printing press to cheap small printing press to print a few cards or things like that. Right. So um, you're not expected to generate a lot of waste or affect the environment in a very large way. So therefore, your project might be screened out. But whereas other projects that are such as that are much bigger and might have bigger impacts, such as a big dam, are things that will be screened in for environmental impact assessment. Then the second step is scoping to identify which potential impacts are relevant to assess. So basically for a dam, what all things do you need to assess? If that area has a lot of earthquakes that are happening, then you need to assess if whether creating a dam will lead to an increase in the uh, number of earthquakes that are happening, or will lead to an increase in the magnitude of the earthquakes that happen. Right, because dams are known to create earthquakes. Like increase propensity for earthquakes. Uh, then other things such as how much uh, basically area is getting disturbed, or if how much area is getting submerged, how much water is getting affected downstream, and things like that. Right. So scoping to identify which potential impacts are relevant to assess, to identify alternate solutions that avoid, mitigate, or compensate adverse impacts of biodiversity. So things such as, let's say if this dam is too destructive, or maybe is planned to happen in a place which has very high frequency of earthquakes, then people like we might decide not to even proceed with the development. Otherwise, we can try to find alternate sites or designs which avoid these impacts, or we can implement safeguards in the design of the project for or provide adequate compensation for the adverse impacts. So let's say we move everyone who is staying in that village to another village nearby where there's less propensity of earthquakes, and we build houses for everyone. Right. Like that's something that can be proposed. And finally, to derive terms of reference for the impact assessment. So basically, they'll have some reference values of how this project is going to impact the environment, and basically uh, check these impacts if they're going according to the reference. The next stage is assessment and evaluation of impacts and development of alternatives to predict and identify the likely environmental impacts of proposed project or development, including the detailed elaboration of alternatives. So here is where you basically talk a lot more about alternatives, and you basically identify what are the likely ecological or environmental impacts and how we can basically deal with them. Then you report this whole thing, whatever you carried out in during scoping and assessment, to basically in a report which is called the EIA report or the Environmental Impact Statement, which is EIS. Uh, it also includes the Environmental Management Plan (EMP) and a non-technical summary for the general audience, so that the general people who are staying in that area also understand what is going to happen, what is the proposed development plan, and what are the mitigation strategies for the disturbances or nuisances that it's creating. Then the fifth step is reviewing of EIS based on the terms of reference that was done during scoping and public participation. So basically, we want to know what's the public opinion, whether people are happy with the dam here, whether people think it's good, it's bad for them, and basically involving them and the authority into the decision making. And then finally, decision making, whether to approve project or not and under what conditions. But this is not the final step. The final step is, even after we have decided to proceed with the project, monitoring, compliance, enforcement, and environmental auditing. So basically, we are monitoring whether the predicted impacts and the proposed mitigation measures that were defined in the management plan, EMP, are basically working. Verify if the company or the area or the developer is basically compliant with the EMP, to ensure that there are no unpredicted impacts or field mitigation measures. And basically, if there are something like this, it should be addressed in a timely fashion. So uh, recently, there has been a push for what is known as clean technology. So clean technology refers to any process, product, or service that reduces negative environmental impacts through significant energy efficiency improvements, the sustainable use of resources, or environmental protection activities. So basically, any process, product, or service that reduces negative environmental impact by sustainable use of resource, environmental protection, or by energy efficiency improvement. So there are different themes based on this in clean technology, such as renewable energy, where we generate energy from um, renewable resources such as solar, wind, and geothermal energy. Water purification, so that clean water is available for everyone. Air purification to reduce the effects of air pollution. Sewage treatment, again managing waste. Solid waste management. Environmental remediation, where we basically go back and fix whatever negative changes have occurred in the environment. For example, like converting mined area into a marshy pit, or developing it into a new habitat, or planting trees in place of that, and things like that. Energy conservation and appropriate sustainable technologies. So basically, technologies that basically are appropriate for that scale at which we are working. Right. Here are some examples of some clean technologies. So basically, you can go over these. I'll just broadly tell what all things are there. So the first major thing in clean technology is environmentally friendly energy and energy storage, which includes power generation with renewable energy, such as solar, geothermal, or wind energy, bioenergy, sewage gas, and stuff like that. An environmentally friendly use of fossil fuels, such as combined cycle power plant, where basically instead of having only one turbine, you have multiple turbines. So, for example, let's say you are using coal to heat up water, and you're basically heating up water here and sending it to a turbine room here. What you do is, whatever steam is left out of here, you put it into another uh, vessel of water, which also induces boiling. Then you put the steam into another turbine, right? We can put steam here from another turbine if it is sufficient. And also basically having this assembly of several engines that increases the efficiency. So the amount of heat that is generated, that is also um, not getting lost. Cogeneration power plants where basically you're generating electricity and also heat, especially for colder regions such as Russia or Japan. Like high performance power stations, then CO2 reduced power stations, and there are other things such as storage technologies of how to store these energy efficient grids for efficient distribution. Then circular economy, which includes waste collection and transport, waste utilization, uh, uh, such as basically recycling, thermal waste treatment, then waste disposal, disposing waste such as there's no contamination or hazardous waste, then reduction or utilization of landfill gas that is produced in a landfill, environmental remediation such as land rehabilitation, as we talked about, like in the case of mining operations, where basically they have to rehabilitate the land after once mining is done, ecological restoration, similar themes. Then we have sustainable water management, where basically we talk about water procurement and treatment, water purification, monitoring of groundwater, then water utilization sustainably, such as like efficient distribution to distribution grids, and basically, yeah, efficient increases in water utilization, such as water efficient technology in both commercial and residential sectors. Then sustainable mobility, which is like movement, such as alternative fuels to fossil fuels, so that there's a lot of pollution, such as biofuels, electrical cars, fuel cell cars, which use hydrogen. Then alternative drive technology such as efficient engines, environmental friendly vehicles that produce less pollution. So like things like this Bharat stage 1, 2, 3, 4, that certification that the government gives, or basically Europe has its own standards that basically uh, restrict how much pollution or how much gases should be emitted, can be emitted from a given vehicle. Right. Then traffic control infrastructure such as like uh, electric charging stations, CNG refueling stations, so that people adopt these technologies more and more. Then sustainable mobility management such as carpooling, right? Uh, Resource and material efficiency such as um, what is it, technology, cross-sectional technology, which is basically technology, interdisciplinary sciences, which basically increases the efficiency of different fields of science, such as biotechnology, nanotechnology, development of new materials, such as bioplastics and compound materials, which are less degrading to the environment. Then material efficient processes, such as like we are able to produce more and more materials with less amount of resources, or we are wasting less and less resources. Sustainable design, so things such as eco design, where we are basically applying an approach to design products with consideration for like environmental effects of the product during its whole life cycle. So basically designing these uh, biodegradable plastic bags that can be reused, but like if you throw it away, it will degrade in a very short amount of time, right? Then life cycle assessment, as we talked about before, assessing the positive and negative externalities of things while considering their cost. Then energy efficiency, such as mm, efficient production processes, such as efficient engines, recovery of heat, because generally when we are producing any kind of energy such as light bulbs or even like um, electrical energy, we are generating a lot of heat. So recovery of that heat is also some theme where things are happening for clean technologies. Then we have efficient appliances and energy efficient buildings, such as technical equipments and building equipments, which are more environment friendly and basically reduce the energy usage. So yeah, these were some clean technologies and basically things where sustainable development is going happening right now. So that's it for this week. So we first talked about Yeah, we first talked about how uh, we humans are impacting the earth more and more, and what are the different ways in which we impact the earth, how can we quantify that. Then we saw how the different quantify that impact based on the population affluence and technology, and we saw how population affluence and technology, all of them are growing, and how we because of that our impact is growing. Then but there are also certain technological advancements that are leading to a uh, more managed impact or lessened negative impact on the environment. Then we have population growth rates that are declining. Then, what do you say? We talked about the Malthusian growth model and how it might be correct, but it's not. And so there are different criticisms, such as mm, population growth is not exponential, but it's slowing down due to demographic transitions. Agricultural growth is exponential instead of arithmetic because of introduction of new technologies. Then and introduction increase in the production yields. Then it also does not incorporate that new land becomes available. So the amount of land that is used for agriculture, cropland, and pastures is exponentially increasing. Then neglects the role of technology because this technological advancement is what leads to increased yields and basically um, increased um, yield and basically increased amount of resources. So this leads to the exponential rise of resources and yeah, reduces the land requirement for producing the same amount of material, uh, same amount of resources or crops or livestock. Then there are other criticisms we discussed. And then we talked about sustainable development. We talked about the production possibility curve and how we have choices between affluence and environment. And sustainable development encourages us to take choices that are more towards the environment and less towards affluence. Then we talked about the three pillars of sustainability: environmental sustainability, social sustainability, and economic sustainability. And we talked about the triple bottom line. We talked about weak and strong sustainability. How are they different? We talked about what is happening, how sustainable development goals are set. And we talked about environmental impact assessment, clean technology, and some examples of clean technology. Does anyone have any questions or doubts? Okay, so we'll stop here. We'll meet in the next week. Thank you for attending. And yeah, next week we'll discuss ecology of change, which includes climate change, plastics, biodiversity, and oil spills. Thank you. Bye.